Hello everyone. Today we are going to study class 10th chapter force. In that first topic is translational and rotational motion. Let's take example of rigid object spinner and car. In physics, word rigid means on applying force we cannot change the shape or size of this object. That is, we cannot change the intermolecular distance of the particles. Now, here spinner is an object which is fixed at its center, whereas car is free to move, not fixed at any point. Now I am going to apply force of equal magnitude to both the objects and in same direction. What did you observe? We observed that on applying force, spinner started moving around this fixed point. So such a motion is called rotational motion. And on applying force, car started moving in the direction of force. Such a motion is called translational motion. Very important is, in rotational motion, all the particles of this object are not covering equal distance in equal interval of time. But in case of a car, all the particles are covering equal distance in equal interval of time. So this motion is also called as a linear motion. Translational motion can be rectilinear or curvilinear. So from the examples what we have observed, when a force acts on a stationary rigid body which is free to move, the body starts moving in a straight path in the direction of force. This is called linear or translational motion. Now let's see certain examples of translational motion. A moving car, an apple falling from the tree, ball moving on the ground, moving train. In all these examples, direction of force and direction of motion same. Direction of gravitational force, direction of motion of apple same. Direction of force and direction of motion are same for all these examples. Next is rotational motion. So if a body is pivoted at a point, right? So body is fixed at a point and the force is applied on the body at a suitable point. It rotates about the axis passing through the pivoted point. This turning effect of force and the motion of body is called rotational motion. Now let's see certain examples of rotational motion. In this case, this is the fixed axis about which it is rotating. In this case, there is an imaginary axis about which it is going to perform rotational motion. Here in this case of merry-go-round, here is the fixed point. In this case, this is going to be the fixed point about which he will perform rotational motion. Right? Next example is Earth, rotating about an imaginary axis passing through its center. Then, what are the conditions for translational and rotational motion? Condition for translational motion is rigid object should be free to move. Free to move means it should not be fixed at a point, right? And the condition for rotational motion is object should be fixed at a point. Clear? Now let's start with the topic moment of force, also called as torque. Now let's focus only on the object which is fixed at a point. Turning effect which is produced by our force is called as moment of force. That is, how much is it turning? This turning effect of force called as moment of force is also called as torque. So, concept clear? Now let's focus on the measurement of moment of force. There is no direct device for measurement. So we have to focus on formula. Let's derive it. Moment of force is equal to, let's fill this blank here. Imagine this door with three handles A, B and C. This is the fixed axis about which door is going to rotate. Now, I am going to apply three different forces to this handle A. First time, I am applying 10 Newton force to handle A. You observe turning is maximum. Second time, I am applying 5 Newton force to handle A. Turning was little less than before. Third time I am applying only 2 Newton force. Turning was minimum. So what is the first factor? First factor is force. Moment of force is equal to force multiplied by. Now let's find out the second physical quantity. We are going to apply 10 Newton force. That is same force to all the three handles A, B and C. Let's see. First time 10 Newton force to handle A, turning is maximum. Second time 10 Newton force to handle B, turning is little less than before. Third time same 10 Newton force to handle C, turning is minimum. So what matters is this perpendicular distance between the pivoted point and the point where you are applying force. That is line of action of force, right? Perpendicular distance of handle A is maximum. Perpendicular distance of handle B is little less than A. And perpendicular distance of handle C is minimum. Perpendicular distance between line of action of force and the axis of rotation, right? So what is the next factor? It is perpendicular distance of force from the pivoted point. Clear? So we got our formula. Moment of force is equal to force into perpendicular distance. Now, what are the factors affecting turning effect? First, magnitude of force. Second, perpendicular distance. Now, after measurement, we need units. Why to remember units? Instead of remembering, we will be deriving the units. See how. Moment of force, formula is force into perpendicular distance. Now, let's give unit to force and let's give unit to distance. So we will be able to derive our units. Force, SI unit is Newton, multiplication sign. Distance, SI unit is meter. Newton meter is the SI unit of moment of force. Now let's go for CGS unit. Force, CGS unit is dyne, multiplication sign. Distance, CGS unit is centimeter. Now I want to go for gravitational units, right? So gravitational unit of force in SI system is kgf, multiplication sign. For distance in SI system, unit is meter. Gf, gravitational unit in CGS system, multiplied by CGS system distance unit is centimeter, right? Now we want to study what is the relationship between dyne centimeter and Newton meter. Next, we are going to derive the relationship between kgf meter and Newton meter, starting with the bigger unit. Now, split this Newton meter into two parts. I have taken 1 Newton meter. So, 1 Newton multiplied by 1 meter. Clear? Now, convert this into CGS system. So 1 Newton is equal to 10 raised to 5 dyne multiplied by 1 meter. It is equal to 10 raised to 2 centimeter. Clear? Now 10 raised to 5 into 10 raised to 2. So 10 raised to 7 dyne centimeter. Clear? 1 kgf into meter. It is equal to how many Newton meter? So 1 kgf into meter, 1 kgf multiplied by 1 meter. 1 kgf, it is equal to 9.8 Newton multiplied 1 meter. Multiply this, so it is going to be equal to 9.8 Newton meter. So 1 kgf meter, it is equal to 9.8 Newton meter. Clear? Moment of force is a vector quantity. It means turning has some direction, right? So turning effect can be anti-clockwise, clockwise. So anti-clockwise moment or clockwise moment. Anti-clockwise moment is always taken positive and clockwise moment is always considered to be negative. Clear? Let's study how to change the direction of rotation of an object. For this, consider this object having ends A and B. I am going to apply force in same direction at the points A and B. If I apply force in upward direction at point A, it produces clockwise turning effect. What if I change the point of application of force? That is here in upward direction first time. Second time, I will apply force in upward direction at point B. So which turning effect did you observe? Anti-clockwise, right? So how can we change the direction of rotation? By changing the point of application of force. Second method, I'm going to apply two forces at point B. First time I'm applying force in upward direction. So I got anti-clockwise turning effect. Second time I will apply force at same point in downward direction. So I'm getting clockwise turning effect. So what is the second method? By changing the direction of force. Same concept could be understood from this diagram. Just by changing the point of application of force. Initially force is applied at A. So we are getting the movement of this disc in anti-clockwise direction. Now instead of A, if we apply force at point B, then now disc will start moving in clockwise direction. Clear? So just by changing the point where we are applying force, we can change the direction. Next is, in this disc, point of application of force we are keeping the same. First time we are applying in upward direction. Second time we are applying in downward direction. Here we are getting anti-clockwise moment and here we are getting clockwise turning effect, right? By changing the direction of force. Let's study certain examples of moment of force, which is to open or shut the door. So with minimum force, we can get maximum turning effect if we are keeping perpendicular distance maximum. Next is circular hand floor grinders are having two circular stones. So why this handle is always provided near the rim of this first circular stone? Because we need to keep this perpendicular distance maximum, right? So as to get maximum turning effect with minimum force. Steering of your car, you are applying force on the rim of the steering so as to keep maximum perpendicular distance, right? For getting maximum turning effect with minimum force. You are always applying force on this foot pedal. Why? More the perpendicular distance, with less force you can get more turning effect. In this spanner, if here is the nut which is to be loosened, at which point should we apply force? A, B or C? Definitely C. Why? So that with minimum force we can get maximum moment of force. Conclusion. Larger the perpendicular distance, less is the force needed to turn the object. Clear? Next topic is couple, which is actually required for rotational motion. Single force does not cause rotation of a pivoted object. So always we need two forces, that is pair of forces for producing rotation. Now any two forces are okay? No. We need special forces which are equal in magnitude, opposite in direction, parallel to each other, and which are not acting along the same line. If two forces satisfies this condition, then that pair of force forms a couple. Let us consider this object having ends A and B and which is pivoted at its center. We want to rotate this object. So we are going to apply pair of forces. Two forces, F1 and F2. Both are equal in magnitude, 5 Newton, 5 Newton. Opposite in direction, F1 downward and F2 upward, right? You can see they are parallel to each other and they are not acting along the same line. According to definition, two equal and opposite parallel forces not acting along the same line forms a couple. Rotation of door is produced by two forces. But you might be thinking that in our day-to-day life, we apply force only at one point. Then the force which we exert at the handle of the door is actually an action. And to that reaction is equal and opposite, just generated at the hinge on its own, right? So again here in case of door, action and reaction forms that pair of forces which is responsible for rotation. So for rotation, compulsory two forces are required. Examples, car wrench. You might have observed this device wherein we are applying force at two different ends, right? Which forms couple. You know that one force will be applied in upward direction, other force will be applied in downward direction. You are well versed with this diagram. On steering of a car, we apply forces which are equal in magnitude, opposite in direction. Now, let's talk about formula for finding moment of couple. For deriving formula, we are taking an object AB which is pivoted at point O. Now we are applying two forces, F at point A and F at point B. Distance between AB we have taken is D. This distance is also called as couple arm. Now these two forces are equal in magnitude and opposite in direction. So they are forming couple here. We will start with what we know. We know moment of force formula, right? So we will calculate moment of force for end A, moment of force for end B. Moment of force at end A is equal to force multiplied by this perpendicular distance between pivoted point and line of action of force. So it is OA, F into OA. It is producing anti-clockwise moment. So we have written the direction here. Now moment of force at end B, that is equal to force multiplied by this perpendicular distance OB, right? So F into OB. That is also anti-clockwise. Now as both the directions are same, we got to add them up. So total moment of both the forces, which is actually called as moment of couple. Add them up. So F into OA plus F into OB. Take F common. So we are left out with F into OA plus OB. What is this OA plus OB distance called as? It is equal to D, called as couple arm. Now moment of couple formula we got F into D. What is F? Either force, means any one of the force, multiplied by which perpendicular distance? Between two forces. Now units of moment of couple. SI unit Newton meter, CGS unit Dyne centimeter, gravitational units kgf meter and gfcm. These units are same as that of moment of force or torque. Our next topic is equilibrium of objects. Let us consider this object which is free to move, not fixed at any point. If I am applying force F1, it starts moving in the direction of force. So it starts performing translational motion. So it is not in equilibrium. Consider this object which is pivoted at its center. I am going to apply two forces equal in magnitude, opposite in direction, parallel and not acting along the same line. What did you observe? It started performing rotational motion. Now to the same object which is pivoted at its center, I am going to apply two forces which are equal in magnitude, opposite in direction, but the point of application is different. So on application of force, object is not changing its state of rest. In spite of forces acting on it, no change in its original state. So object is said to be in equilibrium. So from the example we understood, when number of forces acting on the body produce no change in its state of rest or of motion, the body is said to be in state of equilibrium. Equilibrium is of two types: static equilibrium, dynamic equilibrium. Let us understand this. Imagine any object is in state of rest. We are applying so many forces to it. Still it continues to be in the same state of rest. Then it is said to be in static equilibrium. And if object is initially moving with constant speed and in particular direction, we are applying so many forces. Still it continuously moves in the same direction with same speed. Then we can say it is in dynamic equilibrium. Let's study static equilibrium in detail. For that we will take this example. Consider this block. We are pulling this block towards right with force 5 Newton, and we are pulling towards left as well with same force 5 Newton. What will be the observation? Block will not move. That is, block is at rest because forces are cancelling each other as they are equal and opposite, right? So in spite of forces acting on it, it is not changing its original state of rest. So it is said to be in static equilibrium. So what's the definition? When the body remains in a state of rest under the influence of several forces, the body is said to be in static equilibrium. Next example is a beam balance. On this beam, we are applying force F1 by keeping the standard mass. This F1 force produces anti-clockwise moment, and right pen we are putting some unknown mass here which is applying force F2 on this beam. This F2 produce clockwise moment, right? If this anti-clockwise and clockwise moments are equal, the beam will be in balanced position, right? So if forces are same, we will get beam in static equilibrium. Next is a book lying on a table. Let's think of which all forces are acting on this book. Force applied by book on the table, which is equal to the weight of the book, which is in downward direction. Force of reaction applied by table on the book in upward direction. As both the forces are equal and opposite, they cancel each other. So book is in state of rest. So book is in static equilibrium. Now dynamic equilibrium. Imagine an object which is moving at a constant speed in particular direction. In spite of several forces acting on it, it continues to be in same state of motion. Then it is in dynamic equilibrium. First example of dynamic equilibrium is raindrop reaching Earth's surface. In case of a raindrop, let's see which all forces are acting on it. First is the downward force, is its weight due to gravity. Upward force, frictional force applied by air molecules. In case of fluids, frictional force is termed as viscous force. Upward force, we have buoyant force applied by air molecules, right? In this case, if we add up friction and buoyant force, then we will get the sum exactly equal to the weight of the raindrop. This is true only due to the shape and size of this raindrop. So in short, upward forces cancels the downward force. So raindrop keep falling with constant velocity and it is said to be in dynamic equilibrium. If we are whirling this stone with constant speed, then in spite of forces acting on it, it continues its motion with constant speed and in particular direction, right? Here tension in this string provides necessary centripetal force. Next example is motion of an electron. Here electron, in spite of force which is applied by nucleus, it continues its motion with constant speed. So we can say electrons are in dynamic equilibrium, right? Here in this case, electrostatic force of attraction of nucleus provides necessary centripetal force. Next example is aeroplane. When aeroplane is moving at constant height with constant speed for certain interval of time, at that time we can say aeroplane is in dynamic equilibrium. See, four forces you can observe. Upward force lift, downward force gravity, that is the weight of this aeroplane. Forward force thrust, backward drag, right? They all are cancelling each other. So in spite of four forces acting on the aeroplane, it is moving at constant height with constant speed. So aeroplane in dynamic equilibrium. Now the most important topic is conditions of equilibrium. When can object be in equilibrium? When resultant of all the forces acting on the body is 0. Then and then only it will be in equilibrium. Let's consider this object is in state of rest. We are applying three forces F1, F2, F3. In spite of three forces acting on this object, it is remaining in state of rest. Why? Because if you add F1, F2, F3 with their sign, considering the directions, right, you will get the answer 0. So it is in equilibrium. Next is algebraic sum of moments of all forces. So as we want to talk about moments, we are taking an object which is pivoted at a point. Consider a beam which is pivoted at its center. Now if we use the standard mass, then weight of this object applies force on the beam and it produces clockwise moment. Whatever be the distance from the pivot, at the same distance we are keeping an apple on the left side. Mass of apple is similar to this standard mass. Then we will get force applied by apple on the beam which is equal and it is going to produce anti-clockwise turning effects. So in this case, clockwise moment is equal to anti-clockwise moment, right? So if you add these two moments, you will get your answer 0. You know this, that we are taking anti-clockwise moment positive, and clockwise moment negative. And as both are equal, we are getting answer 0. So what is our second condition? Algebraic sum of moments of all forces acting on the body about a point of rotation should be 0. First condition was for translational motion. That is object which was not fixed at a point, free to move. And second condition is for an object which is pivoted at a point. So it is for rotational motion, right? Now let's start with the next topic, principle of moments. For understanding principle of moments, let us consider this scale, which is pivoted at 15 centimeter mark, that is its center. Now 5 centimeter from this point of suspension, I have suspended weight equal to 100 GF, right? This 100 GF weight is producing clockwise turning effect in this scale. Left side to this point of suspension 5 centimeter, I have suspended a weight 50 GF. Now this 50 GF tends to produce anti-clockwise turning effect in this scale. I want this scale in equilibrium condition. How much is the clockwise moment which is produced by this 100 GF? So force 100 multiplied by distance 5. So 500 GFcm is the clockwise moment, right? And what is anti-clockwise moment? 50 GF and this 5 centimeter. So it's 250 GFcm on left side. So 250 GFcm is our anti-clockwise turning effect. Now if I want this scale in equilibrium condition, that is exactly horizontal, there are two ways out. First, either I can change force or I can change distance. First time, let us change distance and check out. Now, instead of 5 centimeter, we have increased the distance to 10 centimeter. So, our L2 is equal to 10 centimeter and mass remains the same. So, force will be 50 GF. So, how much is the anti-clockwise turning effect? It is 50, force multiplied by distance is 10. So, 500 GFcm. So, now we got anti-clockwise moment also 500 GFcm. So, clockwise moment is equal to anti-clockwise moment in equilibrium condition. Clear? This is the principle of moment. Now, second method is we are keeping distance as it is. That is, initially we kept it on 5 centimeter from the point of suspension. Again, we have kept it at 5 centimeter. But this time we have increased the weight here. Clear? So, our force, initially it was 50, now it is 100 GF. Right? So, how much is our anti-clockwise turning effect now? It is force multiplied by distance. So, 100 into 5. So, it is going to be again 500 GFcm. So, we got again clockwise moment is equal to anti-clockwise moment. What is the principle of moment? W1 L1 is equal to W2 L2. So, from the example we have understood, according to principle of moments, in equilibrium, sum of anti-clockwise moments is equal to sum of clockwise moments. So, when this is true, object will be in equilibrium. Next, we are going to verify what we have studied. Verification of principle of moments. This already we have understood from that example, but now let's see theoretically. Scale pivoted at its center O, two weights W1 and W2 suspended at ends A and point B. L1 is the distance of weight W1, L2 is the distance of weight W2. First of all, which weight is producing clockwise moment? W1 produce clockwise moment and W2 produce anti-clockwise moment, right? So let's calculate. Clockwise moment is equal to force multiplied by distance. So W1 L1, right? Then anti-clockwise moment is equal to W2 multiplied by this perpendicular distance L2. So anti-clockwise moment W2 L2. In equilibrium, what is the condition we have observed from that practical? that scale or this meter rule will be horizontal only if W1 into L1 will be equal to W2 into L2. So clockwise moment equal to anti-clockwise moment. So our principle of moment is verified. One of the practical application of this theory is beam balance or physical balance. Now let's study the topic center of gravity. Knowledge of this topic helps us balancing the objects. For understanding center of gravity, let us consider this irregular shaped object. Every object is made up of so many particles. Each and every particle has its own weight, which is acting in vertically downward direction. Weight is nothing but the force with which the particle is attracted towards the center of Earth, right? Now, if I add up weight of all the particles, then I will get the weight of whole object, right? The question is, at which point is this weight of whole object acting? That point is called as center of gravity. What is it called as? It is called as center of gravity. Weight of whole object is concentrated at this point. Now, let us try to understand it in different manner. I am fixing this object about this point, right? Then weight of all these molecules will tend to rotate this object in anti-clockwise direction, right? And weight of all these particles will tend to rotate the object in clockwise direction. Now this point is located such that about this point, anti-clockwise moment produced by these particles will be exactly equal to the clockwise moment produced by these particles, right? So your object will be in balanced condition. Clear? Now if I add up the anti-clockwise moment and the clockwise moment with a sign, right? Then I will get the sum 0. About center of gravity, sum of clockwise moment and anti-clockwise moment will be exactly equal to 0. This is an imaginary point which exists within all the particles and all the objects. So, definition is, the center of gravity of a body is the point about which algebraic sum of moments of weights of all the particles constituting the body is 0. The entire weight of the object can be considered to act at this point, howsoever the body is placed, right? So weight of whole body is concentrated at its center of gravity. There are 3 important notes. First one, the position of center of gravity depends on its shape. Let us understand this with example. I am taking a wire, grey colored wire. Where is the center of gravity of this wire? Here, right? Now, if I turn this wire into a ring, center of gravity is shifted. Center of gravity position depends on the shape of the object. Same wire converted into a ring, but the position of center of gravity is different. That truly depends on distribution of mass of particles in it. Clear? And center of gravity changes if the body is deformed. That is, if you change its shape, definitely its center of gravity will shift. Second note is, it is not necessary that center of gravity always be within the material of the body. Not necessary. We have seen the example of a ring. Material of the ring is grey colored part, but center of gravity is in air, right? So make sure it's not necessary that it should lie within the material of that object. Clear? The same is true for hollow sphere as well. Third important notice, by the concept of center of gravity, body of weight W can be considered as that point particle having weight W. Next is center of gravity of some regular shaped objects. Let's take one by one. First is rod. Midpoint of rod. Yes, circular disc, geometric center. For hollow sphere or solid sphere, geometric center of sphere. Solid or hollow cylinder. For cylinders, we need to draw their axis, right? So midpoint of the axis of cylinder, right? For a solid cone, at height h/4 from the base on its axis. For cone, you have to draw its axis, and h/4th part from the base lies its center of gravity. For hollow cone, you have to draw its axis, then divide that height into 3 parts, then h/3rd part from the base lies its center of gravity. Then for circular ring, just now we observed was center of the ring. Triangular lamina, if we consider page of our notebook, then it is having length and breadth, but thickness of the paper is negligible compared to length and breadth. So as thickness is negligible, we can say it's a lamina. So all the 2-dimensional objects, we call them as lamina, right? So a triangular lamina or a scalene triangle. Point of intersection of medians. Parallelogram, rectangular lamina, square, rhombus. You have to draw 2 diagonals. So point of intersection of diagonals will give you center of gravity. Let's see center of gravity of some regular shaped objects. Circular ring, geometric center, then circular disc, its geometric center, then triangular lamina. So we have drawn here 3 medians, and intersection point of medians gives you center of gravity. Then rectangle. So we have drawn diagonals, intersection point of diagonals gives you center of gravity. Then we have a parallelogram. Again, intersection point of diagonals gives you center of gravity. For square as well, intersection point of diagonals. Then for a rod or a wire, means cylindrical shaped objects. So we are having it as midpoint of the axis. Then next is a cylinder. So see, clearly we have drawn here axis. Midpoint of the axis of the cylinder gives you center of gravity. Now center of gravity and the balance point. This is a very important topic. When a body is pivoted, at its center of gravity lies above the point of pivot. So wherever the tip is, right, just above that, if your center of gravity is, then this object will be balanced, right? If you are keeping this pivot such that it is little bit this side or that side, then definitely you will either get clockwise or anti-clockwise turning effect. But if you want it exactly horizontal, the point of pivot should be exactly below the center of gravity. Clear? Next, we are taking this cube, right? We have pivoted it. So point of pivot should be just below the center of gravity. Then and then only the object will be balanced or in equilibrium. Next is, if you suspend an object, that is, this is a rigid support, and with the help of a thread, we are going to suspend 2 objects. Same 2 objects which we considered in previous slide. I have suspended them, tied them up with a string, right? Then point of suspension should lie just above the center of gravity. Clear? Point of suspension should lie above the center of gravity. Then your object is balanced. If little bit here or there, if you have tied up string this side, what will be the observation? Definitely this rod will be turning in clockwise direction. So you will get clockwise moment. If your string is tied up this side, then we will get anti-clockwise moment, right? So make sure if your point of suspension is just above the center of gravity, object will be in equilibrium. Till now we have discussed only about regular shaped object, but there are so many irregular shaped objects we come across, right? So how to determine their center of gravity? So let's perform a small experiment. It's an irregular shaped surface. Now I have made 3 holes, A, B and C. Okay. Now I have suspended this lamina from hole A. Along with this lamina, I have suspended a plumb line. What is a plumb line? Plumb line is used by mason on construction site for building a wall. They use this for checking whether the wall is exactly vertical or not, as the pointer of this plumb line points exactly towards the center of earth, right? So this string will show you whether is it exactly vertical or not, means perpendicular to the earth surface or not, right? I am going to draw a line on this lamina along the string of this plumb line, right? So from point A along the plumb line string I have already drawn a line. Now I have suspended this lamina from point B, and again I am going to draw a line along the string of this plumb line, right? Because I want exactly vertical direction. Okay. Now from point B I have drawn a line along the plumb line, and same procedure I have repeated for point C, that is suspending from point C, and I have drawn a line along the string of the plumb line. Intersection point of these three lines gives you center of gravity, right? In this case, center of gravity is lying exactly below the point of suspension. Next, important note, for stable equilibrium, this is going to help you out in your day-to-day life. For stable equilibrium of a body, means if you want to balance a body, then its center of gravity must be as low as possible. So you have to adjust such that its center of gravity is as low as possible. Now let's take this example. This kind of a toy you might have observed, right? If you hit this toy, it's going to move here and there, fluctuate, and then again it will come to rest in its original position. If you might have observed carefully in this toy, there will be some sand particles filled in its base. Why? So as to lower down the center of gravity so that it can get balanced condition again and again, right? If we apply force, if we hit this toy, yes, then we will be getting clockwise and anti-clockwise turning effects, but as center of gravity is lowered, it will come back to its equilibrium condition. Clear? One more example for this is buildings, high-rise, tall towers. They are constructed such that their foundation base is made wide so as to lower down the center of gravity so that the object will be balanced, right? Our last topic for this chapter is uniform circular motion, centripetal and centrifugal force. Now let us start with word uniform motion. It means when object or a particle moves with constant speed, uniform speed, then we call it as uniform motion. And uniform circular motion means constant speed in a circular path, right? So when particle moves with constant speed in a circular path, its motion is said to be uniform circular motion. Now let us consider this example. This object is moving in this direction in a straight line. Now if I am pulling this object in this direction with a string, then it will change its path. Initially it was going in this direction, straight line, but now due to my pull, it has changed the direction, right? Again I am pulling it, right? So it was actually going straight in this direction, but again I have pulled it. Clear? As I have pulled it, it started moving in this direction. At every point, if we keep applying force, we keep pulling the object towards the center of circular path, this object will start performing circular motion. So, for the object to perform circular motion, there should be one force which is pulling it and changing its direction every time. So this force which pulls it towards the center of circular path is called as centripetal force, right? So every time for circular motion, centripetal force is necessary. Clear? And if this movement is with constant speed, then we can call it as uniform circular motion. Uniform circular motion is with constant speed, but direction is changing, so velocity is variable. And as velocity is variable, acceleration is changing, right? So the motion is said to be accelerated motion. Next is direction of velocity at any instant. Whatever be the direction of motion of the object, that same will be the direction of velocity, right? Now, what is the direction of motion at every point? If we observe that example, then on a circular path, if at this point, if you draw a tangent to that circle, it will be in this direction. At this point, if you draw a tangent, it will be in this direction. At this point, direction of tangent will be this. So at every point, direction of motion is along the tangent drawn at that point. Clear? So this is to be kept in mind. Wherever you want the direction, you have to draw a tangent at that point. Then you will get the direction of motion, and along that same direction of velocity will also be there. Clear? Now, difference between uniform circular motion and uniform linear motion. Now, in uniform linear motion, speed is constant because it is uniform, right? Linear motion means it is moving, object is moving on a straight path. So, direction is also not changing. So, speed and velocity both are constant. Clear? Whereas in uniform circular motion, as it is uniform, speed is constant. But as it is circular motion, direction of motion is changing at every point. So, velocity is variable, right? Although speed is uniform. Clear? So, here speed and velocity both constant. In this case, speed constant, velocity variable. Now, in this case, as velocity is constant, so definitely acceleration will be 0 because acceleration is rate of change of velocity. Velocity is not changing, so acceleration is 0. In this case, velocity is changing, that is direction is changing. So velocity is variable, so it is called as accelerated motion. Now, centripetal and centrifugal force. So from this example, we have understood object was going straight, but we were applying force to change the direction at every point. This force, which is actually changing the direction of motion at every point, that force is called as centripetal force. So centripetal force is the force acting on a body moving in a circular path in a direction towards the center of circular path or radially inwards. It means along the radius, but inwards means towards the center. Right? Now let's take certain examples. For an electron moving around the nucleus, which force is pulling the electron towards the center? That is the electrostatic force of attraction applied by nucleus. Right? So here in this case, centripetal force is provided by electrostatic force of attraction applied by nucleus. Right? Now next, for a planet moving around the sun, which force is pulling the planet towards the center? That is the gravitational force of attraction of sun, right? So here in this case, centripetal force is provided by gravitational force of sun, right? Now if we are whirling a stone in a circular path with constant speed, then in this case, tension in the string will keep pulling the bob or the stone towards the center, right? So in this case, centripetal force is provided by the force of tension in the string, right? Now, centrifugal force. Let's understand this with an example. This is a path, a road on which car is moving. Imagine you are sitting in this car. Car is taking left turn. Then you are going to lean towards right, that is outward. Okay, so this force which is trying to throw you away from the center of circular path. We call it as centrifugal force, right? So force acting on a body in a direction away from the center of circular path is called as centrifugal force. Let's take one more example. In case of a washing machine, when you put in the clothes are at the center, right? But after the clothes are washed and when you open the lid of the washing machine, what will be your observation after spinning is complete? You will observe that clothes are all stuck towards the side of that washing tub, right? So which force was responsible for throwing these clothes away from the center? That was actually centrifugal force, right? Next, certain important points related to centrifugal force. Centrifugal force is in the direction opposite to centripetal force. Definitely, centripetal is towards the center of circular path. Centrifugal force is trying to throw away from the center of circular path, right? So this pulls the object, this tries to throw the object away from the center of circular path, right? Next, its magnitude is same. It means if centripetal force is 5 Newton, centrifugal force also will be 5 Newton. Clear? So magnitude always will be similar to that of centripetal force. Next is centrifugal force is not a force of reaction. What's the meaning of this actually? You know Newton's third law of motion says action and reaction are equal and opposite. Then see, centripetal and centrifugal are same. Yes, magnitude, so equal, and direction opposite. So these are also equal and opposite. Is this centrifugal force a reaction force of centripetal? No. Answer is no. Why? Because in case of Newton's third law, action and reaction acts on two different objects. But in this case, centrifugal and centripetal forces both are acting on the same object. From those examples what we studied, you understood. Clear? Next is, it is not a real force. Means centrifugal force is not a real force. Not a real force means what? Let's try to understand this from the example. Now let's try to imagine from my words and from this diagram. Imagine this merry-go-round which is actually going to move in a horizontal plane, right? Not vertical but horizontal plane. Person is standing at the center holding a pendulum in his hand, right? Now you are an observer standing on the ground. You are also going to observe the pendulum bob, and the person who is holding it is also going to observe the pendulum bob, right? Now when merry-go-round will start moving, bob will be in this position, right? Now let's observe for a person A who is standing here, right? For him, his face is in this direction, bob is exactly in front of him. When direction of his face changes, again bob is in front of him. Again direction changes, again bob in front of him. Again direction changing, again bob in front of him. It means for this person A, bob is remaining at rest because every time it is in front of his face. His direction changes, along with that bob's direction also change equally. So he feels as if it is at rest. Now in spite of forces acting on it, how can it be at rest? So from this person's point of view, there might be two forces acting. Centripetal force which is towards the center and centrifugal force which is away from the center. So both these forces are cancelling each other, right? Now let's talk about this person's observation, that is your observation. You will observe that bob is performing uniform circular motion. Now when can an object perform uniform circular motion? When object is under the action of centripetal force, right? So for you only centripetal force is acting, and for this person centripetal and centrifugal both the forces are acting. Clear? Now same example we will understand in a different way. You are standing here as it is. Now this person is cutting the string. Now what will be your observation? Observe this. When Bob was here, person A cut the string. Now you will observe Bob will start moving in this direction, right? Now as string is cut, there is no force to change its direction. Clear? So now it has started moving straight, right? Along the tangent drawn at that point where the string was cut. So for you, centripetal force stopped acting. So Bob started moving along the tangent. And what about the person A observation? His face is in this direction, Bob is in front of him. When his face changes, again Bob is in front of his face, but then distance has increased. Again, in this case, direction of his face changed. Bob is in front of him, right? But distance has increased. Again at this position, direction changes. Bob is in front of him, but distance has increased. He will observe that Bob is going straight away from him. So for this person A, initially two forces were acting in first case, centripetal and centrifugal. But as he cut the string, centripetal force stopped acting. So centrifugal force is taking the Bob away from the center of circular path. That will be person A observation. What was your observation in first case? That Bob was under centripetal force and it was performing uniform circular motion. And when string was cut, centripetal force stopped acting and Bob started moving along the tangent. Right? So, person A can explain centripetal and centrifugal both the forces from this position. But person standing on ground can explain only centripetal force. Centrifugal force does not exist for this person. So centrifugal force is not a real force as it cannot be defined from all the positions. Right? So what is the conclusion? That centrifugal force is not a real force. Only force involved is the force of tension, which is providing the centripetal force. Thank you.